Can you hear me? Can you hear me? Louder பேசுறதா இல்ல இதே normal speed? Can I start, sir? Record. Good morning. Today we'll see about microprocessor, PC hardware and interfacing, our subject. I am Dr. Alamilu Mangai. What is a microprocessor? It is a program controlled device. Okay, it's an integrated circuit chip. Okay, it is used in CPU. We know CPU, right? You have your computers, all your computers have CPU. In that CPU, one of the chip is microprocessor. We are going to specialize in learning about 8086 model. There are lots of models available. In that, particularly we are going to see only about 8086, which is our syllabus. Before that, we'll see about the history of microprocessor. Okay, normally the telecommunication era, it is the generation where when the entire telecommunication began. That was during 1970s. Okay, that is the first generation of telecommunication. Exactly, to be precise, 1971 to 73, the PMOS setup was started, and lots of research work happened, and 8-bit, 16-bit processors all came into existence. Okay, second generation, it began in 1973. Alright, in 1973 we have the second generation. In that we have the NMOS setup. Alright, we have the NMOS setup. Those processors were all high speed, little much faster. Okay, that is the thing which they improved. The third generation, towards the end of 70s, around 1980s. Alright, around 1980s, towards the end of 1970th century, it happened. It is 16, again it is 16-bit processors only. So you can remember that during 1970s, that is the telecommunication era. All sorts of telecommunication development in electronics began during that period. In 80s, it was a drastic improvement. Alright, so in the third generation, you have during 1978, again 16-bit processor with 64 pin. The maximum was 64 pins IC chips were manufactured. Fourth generations, I said, in 1980s, peak revolutions of both electronics, telecommunication happened. So in that you have HCMOS setup, and then we have terabyte, gigabyte capacity chips manufacturing. Okay. Fifth generation is the Pentium. So you might have heard about Pentium process. So that is now what do you have? We have the core process, right? In our computers and all, we have the core process. Intel Pentium was the fifth generation. After that, now it is Pentium core process. In that we have i3, i4, i5, i7 and all we have. Isn't it? You all know, isn't it? Okay. So next we will see about the functional blocks. Alright. So what are the components? What are the blocks inside the computer device? So we have the ALU. We have the ALU, which is, what is ALU? It is arithmetic and logic unit. Okay. We have the memory. Memory means what? It is the RAM or the ROM. We have a traditional RAM and ROM, no? So in that we have the registers. Register, what is the purpose of the registers? For storing only. Okay, so register array or internal memory. Next we have the flag registers. What is the purpose of a flag? It is for storing 1-bit information. We have the flag registers. Then we have the decoding unit, and then we have a timer. Clock. You know about clock, no? In our watches, in our phones, TV, everywhere we have a clock. Similarly, our computers or our chips also, our IC devices also have clocks, isn't it? So in that we have time or control unit. Timing and control unit we have. Then we have PC and IP. We have the buses. There are 3 types of buses: control bus, address bus and the data bus, which carry the data. So this is the overview and the history of microprocessors. It was 16-bit 1978, and then around 33% is the internal clock asymmetric source, and then you can store up to 2 power 20 megabytes of memory space. Alright, and we have two modes of operation, that is the minimum mode and the maximum mode of operation. Next we will move on to pins and signals. So we are going into 8086 model, which is having how many pins? It is having 40 pins. It is having 40 pins. So 20 pins on one side and another 20 pins on the other side. Okay, so 1 to 20 is on the left hand side. So 21 to 40 is on the right side. Okay, so we'll see about each of the pins. So the first one is the address bus. Okay, you have AD0, AD1, AD up to AD15. So how many address bus you have? Address bus pins? You have around 16 pins. So AD0 to AD15. So we have how many address bus pins? 16 pins. Okay. Next we have it is the address multiplexed with status. At same address, it is also having status. So you have the pin numbers AD16 to 19, 4 pins. Okay, so AD16 to AD17, AD18 and AD19. So this is similarly address bus. Along with that, you are going to have some signals also attached to it. Alright, yes. Next we have the BHE pin, which is bus high enable pin. Bus high enable pin, that pin number is 34. Alright. It is used to connect upper data. Next we have the maximum and the minimum pin. It is used for mode, setting the mode of the microprocessor. Next we have the read pin. You have a pin for read operation. Okay, it is like you can have values whether it is low or when to read. Like that you can set the values. Next we have a pin for wait. Okay, you have another pin which is 23. It will tell when to wait during the test process. Okay, or you have to wait for some time and then do the test process. For that you have another pin. Then ready. You have a pin for ready, that is 22. Pin number 22 is for ready. In this, whether the microprocessor is ready to accept a signal. Yes, it's in ready state. It tells us about the state of the processor. Okay. Next you have a reset pin, that is 21. This pin is 21. It is for reset. What will happen if it is reset? The already existing values will erase. Next you have another pin 20 for ground. What is the purpose of ground? Connection, earth signal. You have a pin for clock. Okay, pin number 19 is for clock. Basic timing, and you have that signal, symmetric wave signal, it is 33% duty cycle. Alright. Then you have pin number 18, which is used for interrupt request. What is an interrupt? It is when a process is going on, some process comes in. Okay, that is called as interrupt. The existing process, it will take some time to continue. It will not be working, it will stop. We will execute the second process and then it will continue. The first process will continue. That is called as an interrupt. So interrupt, when there is an interrupt, you have you need to give a request. Okay, so for that there is a pin called as 18. This 18 pin is used for interrupt. You have another pin 17. This is for NMI. And next you have VCC volt setting. Then maximum mode, minimum 33 pin is used for setting the operations to be in maximum mode or in the minimum mode. For that, okay. Then you can have you have 33 pin, 31 pin for hold instruction. So when there is an interrupt, the existing process, some process is going on, so that existing process has to wait, isn't it? So when there is a interrupt, so when there is an interrupt, the existing process or the process or the work which is being done, it has to wait for some time. So you wait for how much time? Hold. You're asking to wait, hold. Got it? So then you can use this pin 31. Alright. Next you have 29 pin for write operation. You have read operation also. Okay. For data transmission, we have pin number 27, receive. DT is for data transmission. You want to send the data. Okay. In this DT, R is there, receive is there. Receiving and write, sending. Okay. 2 are there. Then data enable D26. Pin number 26 is for data enabling. And then address latch enable, you are going to multiplex or combine the data with the address. You are going to combine the address with data, that is address line latch enable. Okay. Combining means multiplex and so on. Okay. Next you are going to use memory access. For that you have a pin 29. Next for write operation, the pin number is 29. For pin number 24 you have interrupt acknowledge. What is the meaning of acknowledgement? Acknowledgement is you're going to, when you receive something or when you send us something, you have to send a acknowledgement. It is received, it is sent, like that. So for that, when you receive an interrupt, okay, you have to make the process which is executing or which is currently executing, you have to make it stop. You have to stop that. So for that you have to communicate, revert back. So that is acknowledgement. So whenever there is a process happening, whenever there is an interrupt happening especially, there should be an acknowledge. So for that you have a pin for acknowledgement, that is int A, interrupt A, interrupt acknowledge, pin number 24. We saw about hold and acknowledge. Then we have S0, S1 and S2. These are the status signals. So whenever there is a interrupt or any activity happening, some process is going on, then we need to update the status of the process. So in that you have 0, 0. When S0 is set to 0, S1 is also set to 0 and S2 is also set to 0. It is interrupt acknowledge. Okay, only S0 is set, then it is in read IO port. Okay, when S1 is set, it is write IO. Alright, when S0 and S1 both are set, it is halt. When S2 is set, S1 and S0 are 0, then it is code access. Okay, then S2 and S1 means it is, you are going to write in the memory. When all S0, S1 and S2, all the three are set, then it is passive or inactive. So these are some of the pins and their functions. So when a process is in queue, it is waiting. Then you have some pins QS0 and QS1 to maintain them. You have some other pins RQ and GT. This is for bus request and bus grant, 30 and 31. So when a processor is in working state, you don't want any interrupt, you can lock it. So for that you have pin number 29. Next we will move on to architecture. So in this architecture, this is the architecture of the 8086 microprocessor, full architecture. You have the general registers AH and AL. You have, these are the general purpose registers. Okay, these are the ones with buses which are connecting all the components. Okay, these are the buses. You have three types of buses: address bus, control bus, and then the data buses. Okay, you have some temporary registers, then you have a internal control system, and then the flag registers. You have the instructions which are given. All the instructions are available in the queue. Okay, each instruction will be executed one by one only. So the instructions are stored in the queue. So first one instruction will be executed, and then next instruction will be executed. So from where the instructions, or from where the address data are coming, all that is transmitted or transported with the help of the buses. So the address is carried by the address bus, the data are carried by the data bus, the instructions, the controls, they are all carried by the control buses. So all the units are connected using the buses. There are lots of registers available, each register meant for each purpose. Okay, A for accumulator. Okay, basically the architecture has two parts, that is bus interface unit and then the execution unit. Okay, whichever is communicating with the bus interface unit. The other one is instructions which have fetched by the BIU. Okay, so this part is the one which is having the bus interface unit. This is the execution unit. You have the same architecture in an elaborate manner. So this is a 20-bit address bus. This address bus is 20-bit. Okay. You have 16-bit segment registers, the code segment, data segment, stack segment, and the extra segments. In the memory, okay, I am elaborating how the segments are there in the memory while we communicate with the bus. So in the BIU, bus interface unit. What is BIU? It is the bus interface unit. Okay, in the bus interface unit, how it is there? So you have segment 0, 1, 1, 2, 3, 4. So here, suppose if you are going to store the data in the memory, how in the memory the data is stored. So for example, you can take segment 0 or a portion of data, segment 0 and segment 1, and then see the available space, which space is there in memory. Okay, which available or free space is available in the memory. See that segment size. Okay, the segment size and the available memory size. Try to fit in there. So the system will try to fit in there. If there will be some lapse also, it will not exactly fit into the available space, right? So that will be adjusted, right? So accordingly, here that adjustment is called as overlapping. Okay, if there is some space left over, it will be overlapped. Otherwise, you want some extra space from the extra segment, then that is also you are taking from the other segment. Okay, so here segment 0 data can be fitted into this memory portion, and segment 1 data can be fitted into this portion. But see, there is some overlap. A portion of the second portion of memory and third portion memory is being utilized. Okay, and then some space is taken by the segment 3 also. So whenever there is segment 2 and this segment 3, segment 2, segment 3 is our program or code what we want to store in our in the memory. Okay, this is the physical memory where we want to store. Sometimes there will be some extra space after occupying the memory. There can be some extra space, or sometimes I want some space from the another memory. You are taking the memory from the second segment of memory also, or otherwise the space is available, you utilize the space and then again replace it once it is completed. You replace with another program or another portion of the program. When this has completed its task, you can replace it with the another memory. So that is what is happening here. This is fully overlapping. Okay, so the second portion is completed. So after it is complete, you can remove it, and then in this same space where this portion of program was available, there you can put this segment 3 portion. Okay, occupy this segment. In segment 2 portion, segment 3 can be occupied, program 3 can be occupied. Okay. Now program 4 or segment 4 is it is located somewhere. Now it can be stored anywhere, so it is called as disjoint. There is lot of space available for segment 4. It is freely stored. So you understand how data is being stored in the memory, okay, in the segment registers. Whenever there is a space, it can be overlapped or fully overlapped, partially overlapped and fully overlapped. So these code registers are, all the registers are 16-bit. These code segment registers are 16-bit. You have a pointer to the instructions. Whatever instruction is being executed everywhere, like you have a pointer pointing like what is the current execution, what is the current instruction in execution. So which instruction is now executing. So there is a pointer. What is a pointer? It has the address of the, it has the address of the instruction. This pointer, instruction pointer, will have the address of the execution which is running now, or it is in execution, which is executing now. Okay, so it is an address. It's a address which is being, which is showing the instruction which is executing. All right. So this instruction pointer is 16-bit. Since it's an address, it is 16-bit. Okay, all the instructions are stored in queue. Okay, all the instructions, what you fetch the instruction, and then you first know the address where the instruction is available. You know the address, where is the instruction stored, where it is stored in some memory, where in which part of the memory. You get that address from the instruction pointer. From that you take the address from the pointer. You go to that location, get the instruction and bring it and store it in this instruction queue. Okay, so like that you are having around 6 instructions in this diagram. So 6 instructions are being stored. So these instructions are being stored in the form of what organization? FIFO. So FIFO is first in, first out. So the first instruction which comes inside will be the first to be executed. Okay, the first instruction will be the first to be executed. It is pipeline. It is like in a pipeline. Next we have the decoding execution unit. In this execution unit, all the instructions need to be decoded, which means executed. How it will be decoded? What instruction it gets? Like for example, adding. For adding, you require operator and operands. Okay, if add is an instruction, what is required for add? 2 operators and then two operands and 1 operator, right? So for like that, you have to fetch the operator and then you have to fetch the operands also, right? So like that, how to decode the instruction? Fetch the operands, fetch the operator, execute it, get the result, store the result, then the process is complete. Yes. For example, if you need to do a addition operation, you require an operator and then you require 2 operands. So what are operands? They are values stored in some address, stored in some part of the memory. Where is that address? The address will be there in the address stack. Okay, you need the pointer to know the address. The pointer will point to that memory. From you go to that memory. From there you take the data or the value, operand's value, you bring it here, you bring the operator, keep it, and then execute the process. Add. What is the execution? It is adding. You execute it, you get a result, you store the result in some value or memory space. Where, what is that memory? It is again a pointer, it is again a memory address that will be pointed by some pointer. You are going to store it in that pointer location where the pointer is showing. Store that result there. Okay, then come back, the process is finished. Yes, so this is the work of the execution unit. So to perform these operations you require the arithmetic and the logical unit. This arithmetic and logic unit is 16 bit. So it performs logical also. What is logical? What is logical operations? And or all that also, not just plus minus. So for these we require registers. You have 4 general purpose registers: AX, BX, CX, DX. Alright, and you have some pointer registers, stack pointer, base pointers, and then index registers. In the 16-bit registers you have 8 plus 8. Okay, it is 8x, sorry, AX, which consists of AH and AL. Then you have BX, and in that you have BH and BL. In CX registers you have CH and CL. Then in DX you have DH and DL. So we'll move into the details of the registers. So the first one, AX, is the accumulator register. So what is an accumulator register? Combination of 2. Okay, it is having AL and AL. Okay, in that it is 8-bit plus 8-bit, 16 bits. Okay, this contains low order byte, word, and AH contains the higher order byte. So AL, AH. So A for accumulator, AL, AH, AL, A lower order, AH, A higher order. So A for accumulator, AL is A lower order, AH is higher order. So what is an accumulator? It has the base, it is a general purpose register which stores all the it's used for accumulation, not specific. It does not have any specific task. Accumulator does not have any specific task like adding, subtracting, or memory, like that. It doesn't have a specific task. It can be used for any purpose. So that's why it's called as the accumulator. Okay. Next we have the B register. So A for accumulator, B for base. So it is BX. So in BX we have 2, BL, BH. B for base, BL for base lower order, BH for base higher order. Okay, base register. What is the purpose of a base register? Base, it is the basic. Okay, so it is again a combination of 2, 8 plus 8, 16. Okay, BH and BL, 8 plus 8, 16. Alright, so base register is 16, 8 plus 8. Alright, next, this is used for addressing the memory. This base register is used for addressing the memory. Alright, base register contains the addressing of the memory. Next, we'll go to the C register. It is CX. So we have 2 types, CL, CH. C for counter. We saw A register, A for, in that AL and AH. Next we saw about base register, which contains the memory address. Okay, in that we have BH and BL. Next we are going to see about C register. C also we have 2 types, CL and CH. C lower order, C higher order. Okay, next, what is the purpose of this counter? C register. C register is used for counting. What is counting? Any counting it can do. In the example, previous example diagram, we saw there were around 6 instructions. Instruction 1, 2, 3, 4, 5, 6. Yes. So in that instructions, which instruction is being executed now? Like that, counting can be done for the instruction. it can count the instruction, or it can count, in the example which I gave, adding two numbers. How many operands were there? Two operands. You have to bring two operands. You have to go to the location, take two operands, the values of the operands, bring it and store it. So how many operands? Two operands. So that count. Wherever there is a count involved, wherever there is a counting involved, counting of the instruction, counting of the operands, counting of the steps, counting of whatever is required, so you will be using a counting register or a counter register. So in that you have CL and CH, so higher order and lower order. Again this is 16 bit. Okay, all the registers are 16 bit. Yeah, 8 plus 8, 16. So what executions we can do? Like in shift, mostly the counters are used for shifting. You would have learned about right shift, left shift, shift 4 bits, shift, so 1, 2, 3, 4, shifting. So there you require a counter. Rotation, how many times you have to repeat the loop? 5 times, 10 times, n times. So there you require a counter. Looping. Okay, so these are the areas where you require this C register or the counter register. Next, D register. What are the registers we saw? A register, B register and C register. Now D register, DH and DL. DL, data lower, data higher. Okay, in that we are going to see about this D register. Basically it is the data register. Again it's going to contain 8 plus 8, 16 bits. Okay, you are going to hold 16 bit result. Okay, the data is going to be 16 bit. Next we'll move on to stack pointer and the base pointers. Okay, what is a stack pointer? Stack is a memory. Okay, in that memory you're going to have some things ordered in what order in stack, what order is followed? It follows LIFO. Yes, it follows last in first out format. So you want to remove something from the stack, the topmost one will be removed from the stack. Otherwise the last one will be removed from the stack. It is the offset used for storing instructions. So whatever instructions you want to store, you can store it in this stack pointer. Alright, and it is automatically incremented, and then using the, you want to remove the instruction from the stack, you can say use push or the pop instructions. Push is for putting the instructions into the stack. You want to take one instruction out. Which instruction you will take it out from the stack? The topmost instruction. The instruction on the first, on the top, that instruction has to be taken out. So that is how you do. You use the method called as pop. Pop. You want to put the instruction into the stack, you use push. Alright, so using the push and the pop methods, you're going to insert the instruction into the stack, or you're going to remove the instruction from the stack. Next is the index addressing. In this source index and destination address, the data strings which you use, the data which we use, SI and DI, we have the addresses of the data where it is available. For example, from a memory location 1000 to 2000, you want to take all the data from 1000 to 2000. So what is the source address? 1000. So destination address 1000, 2000. So 1000 to 2000. You're going to remove all the data from that location, from 1000 to 2000. Okay. So to maintain all that, you require this source index and destination index. Next we are seeing about the flag registers. So what is a flag? Flag is also a register. It is also going to store something. Okay, it's also going to store something, but how much it's going to store only 1. Okay, flag is also a register which stores. There are different types of flags: carry flag, parity flag, 0, sign, auxiliary flag, trap flag, and direction flags. So the carry flag, whenever you do some add operation or multiply option, how we have when we get carry over and all, no? So that flag will be set if there is a carry value. Parity flag, you have, this is normally used in network transmissions when whenever there is encryption or decryption done, there you use a parity flag. Here the lower order byte, if it contains even number of ones, then the parity flag is set. The zero flag, if the result is zero, you multiply anything by zero, what is the result? It's always zero, right? So when the result, final result what we get after an operation is entirely zero, then you can set this flag called as zero flag. A number is positive or negative, that can be intimated with the help of this sign flag. Next, auxiliary carry. It is we want to, when you add something, you get numbers higher which you can't store, borrow, add or borrow, okay, then that is those values, extra values are stored in additional carry flags. You have an overflow flag, you get some answer or you get some result which you cannot hold, which this registers cannot hold, output value is too big, then you can store that, you can set this flag as overflow. Okay, the value cannot be held by the 16-bit register, it is beyond that. Okay, then you can set this flag bit saying that it is the value, output value is too big. When you set this flag value, you can understand it's a too big answer. Next is direction flag. The direction flag, for auto incrementing, decrementing purpose, you can set this direction flag. Next is interrupt flag. When a process is execution, you know interrupt is when a process or some job is being executed, instruction is being executed, it is now running. In that stage, another process wants to make use of the memory or the processor. You have to execute the second process. Now the first process has to be stopped. Then you have to set a flag for that as interrupt flag. For that you use the interrupt flag. You set the interrupt flag active. Next is the trap flag. When the interrupt is executed, the mode in which it is being generated, that is captured. So that is the trap flag. So in general, we can have the types of registers into 4 groups. First is general purpose registers. Okay, in that we have AX, BX, CX, DX. All they are 16-bit. Okay. And general purpose registers come in combinations, pairs, isn't it? So the general purpose register exist in pairs, 16-bit. Next we have the pointer register, stack pointer and the base pointer. Next we have the index registers, instruction pointer, segment registers, and then the flag values. Next we will move on to addressing modes and instruction sets. This is a sample program. So microprocessor, how it executes. So for that, this is a sample program. In this, if you see, these are some of the codes, mnemonic codes, mnemonic. Okay, half English, like it will be understandable. It can be understood. Okay, these are all mnemonic codes. Assume, org, mov, move, ax. What is ax? Move ax, accumulator, yes. Okay, mov, move. So you are going to move something from the accumulator, or you are going to move something into the accumulator. So these instructions are, you can understand, if you just read them, you can understand. The codes, they are instructions, they are given as codes. They are in the form of codes, little bit understandable by us. So that is why it is called as a mnemonic code. So another instruction here, JNC. JNC. J for jump. Okay. MOV for move. Add for adding. JNC, jump, jump and carry. Okay. So like this we will see some instructions. What are they? There are many instructions. We will see some instruction sets in other units. So this is a sample program how the instructions are given. You have to write a program like this. So the microprocessor does this work. It will execute this program and it will give an output. Okay, so you have to write a program. In what program you are going to write? You are going to write all the codes in mnemonic codes. Alright? You have two types of languages, Python, Java, all these are all high level languages. Low level languages, assembly language. Okay, so the low level language contains mnemonics. Some can be understood, some codes can be understood, some codes you need to know. So they are all assembly or machine language. Next we will move on to addressing modes. How to address. What is address related to? It is related to memory, something related to memory. Where do we have the address? Memory. What do we have in the memory? Data, instructions, everything that we want to store is available in the memory. So in the memory you have instructions also. For example, you have the operator ABC, you have the operations plus minus division. So all that is stored in the memory only. So you have the operations, you have the operands, all that available inside the memory. So all addressing means it is something related to the memory. So what are the different types of addressing modes available? Okay, every instruction in the program operates on a data. Okay, every instruction we have to write a program, isn't it? In the program we ask the computer or the microcomputer or the microprocessor to do some work. Each step has to be told by us. Instructions has to be given. So each instruction operates on a data. Okay. So each of these data, where is the data available? Data is in the memory. So you need to know the address. You need to know the address of the memory. So how to address these addresses? That is addressing modes. You have register address, immediate address, direct address, register indirect, base address, indexed address, base index address, string address, direct IO address, indirect IO address, and then relative and implied addressing modes. Okay, these are some of the addressing modes. Register address and immediate address, these are addressing modes for immediate data. All this other type of address, comes under memory addressing. This is for IO ports going to the keyboard or to the display, where the output is going to be displayed. It is going to the keyboard. Keyboard is input device. So you are going to enter something now, then it goes to the IO port, keyboard. Output, where do you see the output? It's not a big screen like this, but it's just a small display, LCD display. One small LCD will be there. In that you can see the output. So for that output is that is the output. Okay, next is relative addressing, implied addressing. In this, what are the instructions? In register addressing, registers. For a register, from the register, you are going to store data into the register and going to take it from the register. Okay, first to store inside the register. When you want to use it, you have to take from the register, isn't it? So you have to specify the name. For example, move CL, TH. Okay, this is one instruction. What is C register? C register. What is C register? Counter. Okay, so you are going to move some value into the counter. Okay, from where? From the TH. data. Okay, so you are having a value, say for example, in for loop and all, I equal to 1, I greater than n, okay, I plus plus. So what is the maximum value of I? Maximum value of I. In for loop, I equal to 0, I greater less than n. What is the maximum value of I? N. So what is the maximum value of I? N. Okay, so you are having n. You are shifting that into now CL, counter variable. So you have to count how many times? N times, isn't it? You have to count n times. So like that, you are moving the value of DH into counter variable. You get it? You get it, all of you? So you are moving the value of DH. DH is, say for example, 5. You want to count till for loop 5 times. Maximum value is 5. Until I reach 5, the for loop has to be repeated. You need a counter to count. 1, 2, 3, 4, 5. Yes? So that what is the maximum value? 5 or n. Okay. That value is shifted to CL. CL, what is CL? Counter. Right? You understand? A for accumulator, B for base, C for counter, D for data. That's it. Okay. So you are moving, you are moving the data from counter, that data register to counter register. So what is the instruction you give? A move. MOV is the instruction. Okay. So this type of instruction or addressing is called as register. What is A, B, C, D? Address. Registers. General purpose registers. What is A, B, C, D? They are all general purpose registers. Okay. So register addressing. Register addressing. Next is immediate. Immediate addressing. You want to do it immediately. Okay. So here, what is A? In this example, A. Very good. Accumulator. What you are going to move? You are going to move some value. 0AA 9FH. Say for example, 1000 is the value. Let us not decode that. Okay. You are having a value, and in value 1000, 2000. You have to give me 1000 rupees. I will keep it in my mind. Okay. So immediately I will keep the amount which I lent to you. Okay. You borrowed from me 1000 rupees. Will I store it in my mind forever? Yes. Yes. No. So that like that, immediately it will be there. That is immediate addressing. Some value is being shifted to the register. Okay, 1000 rupees. 1000 rupees you got from me. I'll store it in my mind perfectly, right? So that is immediate instruction. So moving a value, some value, that data is immediate addressing. So how an address is there? Okay, you have 20 lines. At 8086 microprocessor can store up to 2 power 20, which is equal to megabytes of data. Okay, 2 power 20 is 1 MB. 2 power 20 is 1 MB. Okay, so the largest register contains 16 bits. How the actual addressing is? The address which we have is transferred to the bus first. So the address is transferred to the bus which carries the address. So the bus which carries the bus which carries the address is called as the address bus. Okay. Then we calculate any offset is required or not. Okay. How to do the calculation, we'll see. Then each time the processor accesses the memory, the contents are shifted one by one. So whatever from the memory location, you are going to transfer all the data to the address bus. Okay, what is that address? Say number 10 GN mills. That is the address. So you have to shift that value. What is the value? Number 10 GN mills. So you're shifting that value. First, that the door number is shifted. Then the street name or the area name is shifted. Okay, so you are shifting the contents or the address into the address bus. So once it is on the address bus, it will be transmitted. Where it has to reach, there it will go. So how the calculation is done? If there is any offset of data, this is how how the calculation is done. So 89 AB FO0 12. So offset value, if any offset value is available, then you are going to add it, you get a absolute addressing mode. Next we move on to the direct addressing. Okay, this direct addressing is we know the address, we no need to calculate the address. In the previous example, we calculated with the help of the offset value. Now we know the address straight away, so we have to directly move that value to the location. Okay, so we are shifting the address value directly. Say this particular location we want to do something, so you are shifting that value to that location. In this example, bx, so b contains the base values, so in that you are going to, this 1354h is a address. Say for example 10 GN mills, that 10 GN mills address is directly shifted to this base register. Okay, square brackets is used if you want to make it specific. If you don't use square brackets, it will be like a data. Okay, so to say that this value 1354h is a memory address, that value is a memory address, you can put it inside the square brackets. This is direct addressing. Next is register indirect. Okay, we saw about register direct, that is register addressing, and now we'll see about register indirect addressing. Okay, so in this we have to calculate, we are going to calculate the base address. How to do the base address calculation is, suppose we want to move from base register, whatever the content is there in the base, we are moving it to the counter. We are moving the data or whatever is available in the base, memory base address is available in the base, we are shifting that to counter. Okay, how to do the calculation. Okay, next here we are going to see the square bracket. What is the purpose of square bracket? It tells it is the direct address, right? How are we going to calculate? We are going to calculate Bx will be assigned to EA, that is a register accumulator, and then to the base address we are multiplying by 16, and then we are adding the address, base address, and then the accumulator address, and then here we are shifting that value which we received to the counter, and then adding the value, incrementing this value. Okay, this like this we can calculate the indirect addressing method. Alright, here we will see in based addressing, we will see about how the based addressing calculations is done. Same type, you are given with a register address, you are given with a memory address. Okay, we are given with a memory address. In this memory address, what you are doing, you want to shift it to the accumulator. Whatever address is here, you are going to shift it to the accumulator. Here you are going to check whether it is a signed positive number or a negative number. Okay, and then you are converting it into hexadecimal. Then again the same formula, you are going to add it and then increment the counter. So like this you are having the offset value, adding the offset value and finding the base address. So this is based index method. You will have some problems like this also, you have to remember. Next is indexed addressing. Indexed addressing, you are going to find the displacement or the change which is available. Whatever changes or whatever indexed value is added, you are going to find that. Similarly, you are going to check for the sign and then convert it into the values, hexadecimal and then the decimal values, and then add the, okay, Next one is base index method, similar to the previous method only. You are going to check the sign values and then add the offset to it. Okay. This is string addressing method. You are going to find the SI register value and find out the data which is stored, calculate the base address and then move it to the destination. Here the calculation of the source and the memory allocation is given. How you are going to find the destination address, and then you have to shift it to the address. Next is I/O ports. You are going to transfer the data to the input or the output. So you are going to get it from the keyboard, or you are going to display it to the LCD unit. So for that, how to do? You need to know the port address. Okay, the ports where you connect. So you need to know the port address. So you are converting it here and then shifting that to the accumulator. Port indirect addressing. In this port indirect addressing, you are moving the address to the data address. This is an example. Here the instruction pointer is used. So for that you are adding the pointer value. What is there in the pointer? Address is there. So to that you are adding this value and then it's converted. This is implied addressing. What are the operands used? What are the operands used? That we will be seeing this implied addressing. Which are the operands that are without the operator, without the operand, how it is used? There is a carry flag which will always be set to 0 in this. Next we will move on to the instruction set. 8086 microprocessor contains, or it uses basically 6 types of instructions.